Thank you, John. And thank you all for coming out. It's a real privilege for me to be out here. We'll get to that here in a second. So we are going to talk about a graph theory approach to seating people at parties here. Fun title. Let me get this. Oh, there we go. All right. So here's the trailer. Yay, right? So the trailer for this talk is that this is prepared for a general audience, which is part of why I honestly love doing what I do. So graph theory, whatever that is, right? We'll get to that. Is what I do for a living. This is my area of research. This is what gets me excited when I start talking about math and I start talking about graph theory. Talking about math is fun. Talking about graph theory is like, yay! I get all excited about this here. But part of why I really like it is that it's something that in a reasonable amount of time I can actually tell you what I do for actual research, which is really, really, really fun, right? Some other people, in other fields, I mean, you have to read papers and take massive amounts of classes to just understand what the question is, right? Let alone try to answer the question here. So for me, I love doing this. This is a lot of fun here. So the outline of what we'll be talking about today. So we'll start off with a little bit about me, because I like talking about me. I always tell my students at the start of the semester that they're going to know more about me than they ever care to know, right, by the end of the semester. So we'll start off with a little bit about me so we can get that out of the way. And then I'm going to tell you a story. It's not going to be true. It'll be a fake story, right? Just a pretend made-up story that will help motivate the math here. Then a story within a story. Midsummer Night's Dream, anybody? Yeah? Okay, so it's a play by Shakespeare in which the actors in the play then put on a play in the play. It's very meta. All right, so that's what's going to happen here. We're going to have a story, and then the person in the story is going to tell a story. I just thought of it, okay? Anyways, all right. So, and then we'll get to what is graph theory, and why should we care, right? That's always useful. Then we'll talk about mathematical research and how it's like Jenga. You should probably at this point in time be sitting there going, what kind of talk is this? I don't know either. We'll figure this out together. Then we'll get to a true story. That'll be fun. And then we'll get to actual current day research, which some of you may be thinking holy cow, what's going to happen? Especially professors may be he's aiming this way too high. Hopefully not, right? So we'll get to something here, some actual current day research, which I like talks like this. I like giving talks like this where I can sort of build to not just something that's an interesting mathematical topic, but also something that's an interesting mathematical topic that we still don't know all the answers to. Right? So to me, that's a lot of fun. So that's hopefully the goal of where we're going to get to. All right? So let's make it happen. All right. So you probably have absolutely no idea, one, who this person is, or two, the movie. This is Cheech Marin. The movie is what? Oh, no, it's not that one. This is Born in East LA. All right, so Born in East LA. I was not born in East LA, but I am a Southern Californian. I'm very sad. Very, very, very sad Southern California for those of you who do pay attention to sports, but we'll stay away from that, right? I was upset for a long time after the World Series. Anyways, so a native Southern Californian, lived all over the place in Southern California here. Did what any self-respecting high schooler would do out of high school, right? Fast food. Yeah. Would you like fries with that? Right? Hi, welcome to Dairy Queen. How can I help you? I still have that ingrained in me from working drive-through for a year. And then after that, I did what any normal person would do after something like that. I spent 5 years in Central America, in Belize. I know, right? Right? So here's me. Yay. I was teaching junior high and high school math. I could spend hours just telling you how that even happened. I don't even know because I didn't go there to teach junior high and high school math. It just sort of happened. And again, right, high school diploma. So sort of the MO was, hey, if you took high school and passed it, you can teach it. So that's sort of where I was. Did all sorts of crazy stuff. Caught an iguana with my bare hands. That's another story. I don't know if you can see that thing down there. You know what that is? That's not a rattlesnake. It's a snake. They call it lightning snake. And that's a piece of string attached to the snake, and that's an idiot holding it's an idiot on the other end of the string. I don't know why I did this. But anyway, so yeah, there's me walking a snake out towards the jungle just cause. And here's me with some junior hires, and all that good stuff there. So yeah, craziness. I don't know. I was a DJ, a radio DJ for 3 months. I don't know. Crazy stuff happens, right? So did all this here, and at the end of it, realized that I absolutely loved teaching. That for me, that it was something that if anybody wants to teach, I always recommend, I love people who want to teach, and I always recommend to get yourselves in front of some sort of classroom, Boys and Girls Club, YMCA, I don't care, volunteer for something to where you are in charge and start to get that experience. Because you'll realize sooner or later if you really, really like it or not here. I was fortunate enough to have the experience and realize that I absolutely loved teaching. And so when I came back to the States in August of 2005, I did what anyone would do. I worked at a warehouse for a year, right? I hope you've realized at this point in time that my life is not linear, okay? It's been here, 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 here. Long story short, in summer of 2006, I got called into the HR office, and they were like, hey, Mike, you've been really great here. We know that, you're sort of already started looking for other jobs and things like that because the warehouse corporate ladder has 2 steps on it. And I was on the first step already, so yay. And it was like, but we're slow right now, so we're gonna let you go. Awesome, right? So I walked out of there, and oh, here's your last paycheck, right? So we've already calculated it, here you go, right? So I'm walking out, and everybody should have the experience of walking out on the street with like all the money in the world right there in their hands, right? Yay. So it was at this point in time that I figured, I think I'll go to college. And so there we go. So as John was saying, for me, I have a lot of pieces of paper. So I have a bachelor's degree in math, I have a master's degree in math, I have a master's degree in the teaching of mathematics, and I have a PhD in mathematics. But aside from all of that stuff, I also have this piece of paper. So this is my associates in liberal arts. Not even in math, right? It's in liberal arts from Palomar Community College. And I don't say this to be sort of cute or trite. I mean this in all sincerity, that this is my proudest academic achievement. Out of all the things that I have done, proving a 25-year-old conjecture in mathematics, publishing in several different papers, hosting and organizing a conference, being invited to give talks at conferences, this is my proudest achievement. Because what I'm doing right now was not the plan, right? I mean, y'all are here, and you all have some of you maybe have an idea, some of you have no idea. Right, and that's okay, right? The whole undecided is a major, right? It's a major decision. Get it? All right, anyways, I saw it on a t-shirt. Anyways, right, so for me, this was the first step in something that I had no idea where it was gonna take me. And so for me to be here where it was basically 11 and a half years ago, I was one of you, taking my gen eds, English 101, right? Woohoo, right? Poli-sci, yeah. Chemistry lab, yeah. I also took some really, really, really strange class. Oh, music. I took like this music class. That was actually a whole lot more fun than I thought it was gonna be. Right, so that was kind of fun, a music theory class, yeah, right? To satisfy some sort of like quantitative reasoning thing, right? Right? Some of you know what I'm talking about, the whole like, I need to satisfy this thing, that thing, this thing, right? So, all right, that was me. So for me, it's a real pleasure and a real privilege for me to have the opportunity to be here and to talk to you all. And so if you take nothing else away from this talk here, and I hope you do, I'd like you to take away the fact that what you're doing here, you have no idea how it's going to affect you in the future, right? This first step that you all are taking is something that you have no idea what it's going to become and where it's going to go, and it's a crazy, insane ride from this point in time. So you probably won't go to Belize or anything like that, and hopefully you don't get laid off at a warehouse. Right? Hopefully you do better than that. But besides that, from wherever you go, this is a great first step here. Oh, that was nice. Okay, so let's get to math. Yay! Okay. So, and I'm more than happy to talk about any of these and all of these other stories that I told you about afterwards. You're more than welcome to ask me, and I'll tell you. I've seen giant bugs and all sorts of other crazy stuff. Anyways, all right. Out of curiosity, I'm not expecting anybody to know, but does anybody have an idea who this is? I was really surprised about the Cheech Marin one. I'm glad somebody got that. So this is Paul Erdős. So Paul Erdős was a famous mathematician. He passed away about 20 years ago. A very prolific mathematician. If you've ever heard of something called the Erdős number, he is the Erdős from the Erdős number. All right. So now Erdős is a very interesting personality, let's put it that way. as most mathematicians are, right? My friends don't like me saying that. My fellow mathematician friends don't like saying like, hey, we decided to do math for the rest of our lives. Something's wrong with us. And they're like, what? Yeah, they don't like hearing that. Anyways, but so Erdős here has a lot of interesting stories. I'm going to tell you a fake story, totally made up story, right? So this is now we're going to get to the made up story here about Erdős. So here's my made up story. So Erdős, right, it's getting time for the Super Bowl. Erdős decides to host a party and go out and invite some of his fellow mathematician friends, right? Mathematicians at a party, that's a way to go, right? So he goes out and he's like, hey, Super Bowl party, right? Goes to all his friends and says, hey, come on over. We'll have a blast. We'll have a giant dinner. I've got a big old table and all sorts of stuff, and we'll have lots of fun. Now, of course, as parties go, friends invite friends who invite friends, right? And then things start to get out of hand, right? But that's okay. Erdős is a very gracious host. And so all these people are coming at his door that he's like, I don't know who you are, but it's okay. Come on in anyways, right? Plenty of food, all this good stuff. So he's a really nice guy, and he brings everybody in. And you know, while everybody's having a good time, he decides to, like, you know what? He calms himself down sort of in the corners. He's like, it's all right. Make this happen. I got a giant table. This is cool. So what I'll do is, because I'm such a gracious host, and I know that one of the most awkward things at a dinner party is to be sitting next to between two people that you have no idea who they are. That is horrible, okay? It's also not so fun to be sitting at a table and you know one person here, you're friends with this person, you don't know that person, and of course your friend is talking with somebody else, right? And it's like awkward again, right? So Erdős is like, you know what I'm gonna do? I'm gonna figure out who these people know, who they're friends with, and then I'm going to try to seat them around this giant table that I've got here in such a way that each person's friends with the person on their left and the person on their right. So everybody's kind of happy then here. So Erdős, because he's a math geek, goes out and he starts diagramming who knows who. Right? Mathematicians, especially graph theorists, like, this is, yay, exciting for us. So here's Erdős in the middle, right? So he knows a whole bunch of people and things like that. So he's going around like, hey, who do you, you came with this person? Oh, okay, cool, right, yeah, great, great, great. So he starts diagramming this stuff, and all of a sudden, like, he's going crazy because this is getting really convoluted here. So Erdős, being a good mathematician, does what any good mathematician should do. If you are ever faced with a problem that you don't know how to do, try a small example and see if you can do that, okay? So Erdős, this is the story within the story. He comes up with a story. 6 pretend people: Alice, Bob, Clarice, Debbie, Eustace, and Frank. I know these names because I use them a lot, okay? So he decides, okay, you know what? Let's figure out what I'm looking for here, and then maybe if I do this small example, this will help me to actually, you know, seat everybody at this giant table here. So he comes to us with these 6 people, and he says, all right, I'm going to represent each person using a dot. So here's the dot that corresponds to Alice, right? And then Bob and Clarice, Debbie, Eustace, and Frank here. And I'm going to draw lines between the dots if the people are friends, okay? So for example, Alice and Frank, they're friends, so he'll draw a line between them. And then Alice and Debbie, oh, Frank and Clarice, Clarice and Debbie, Debbie, Eustace, Eustace, Bob. Bob and Debbie, this is really testing my knowledge of who these people are, Bob and Frank, and Clarice and Eustace, okay? And that's it, I hope, right? So anyways, so if people aren't friends, then he doesn't draw a line between them. So for example, Alice and Bob, they're not friends with one another. There is a joke here. If you ever take a course in game theory, there's always 2 people who compete, and it's Alice and Bob. It's a funny joke. Ha. All right, anyways, all right. It's really, really funny if you do game theory. Anyways, all right. So Alice and Bob, they're not friends, right? So you see what's going on here, right? Okay. So if Erdős were to slam down this giant oak table in the middle, that's one of my favorite graphics, so we got to do it again, right? Slam, right? Honestly, no lie, this is one of my, I'm like a kid in a candy store with this thing, because it's like, yay, it looks like I'm animating here. I can't draw. So he puts down this giant oak table in the middle of these 6 people and seats them around this way, then obviously this is not what he wants. This does not satisfy the requirements of what he wants to have. I mean, if you look at Debbie, Debbie's happy, right? Because she is sitting next to Eustace and Clarice, and she's friends with both of them. But if you look at Clarice, she's only friends with Debbie, she's not friends with Bob. And Bob is, of course, really unhappy. Not happy, Bob. Anybody? It's okay, whatever. Not happy, Bob. All right, so this is what happens here. So that's a problem. So what in the world is Erdős going to do here? Well, if you take a look at this diagram that Erdős has, you'll notice that here, Alice and Frank, they're friends. Well, Frank and Clarice are friends. Clarice and Eustace are friends. Eustace and Bob are friends. Let's see, Bob and Debbie and Alice are friends. It's kind of cool. So we have this sort of cyclic structure that spans all the people at the party here. So let's start to shift people around here. So if we take Bob and Frank and switch their positions, this is what we get. Let's see, if we take, I think it's Debbie and Eustace, if we switch them, this is what we get. And then if we take Debbie and Bob and switch them, this is what we get. So by rearranging the people, all of a sudden here you can really easily see the cyclic structure here. So if we slam the table down right in the middle of them and arrange them this way, this is exactly what Erdős wants, okay? And we will call this structure a cycle of friends, in particular a spanning cycle of friends, all right? So this is a cycle of friends, and by spanning I mean that it has everybody in the party, okay? So this is cool here. So this is what Erdős realizes, this is what he wants. Now this structure here, this bunch of dots and lines, this is a graph. Now I know what you may be thinking. I know what graphs are, right? Y equals x squared, right? Y equals mx plus b, all that sort of stuff. No, no. For the purposes of this talk, and some of you may be happier than others with what I'm about to say, until, what, 3, you can completely forget that these things are graphs. So yay, right? You hit the dump button for the moment here, and then you have to recollect it at 3, okay? These, when I say the word graph in this talk, I don't mean this, okay? A graph, for my purposes here, is this thing here. A bunch of dots and lines where between every pair of dots there's either a line between them or there isn't, okay? So this is a network. This is essentially what this is representing, is a network of objects here. That's what we're talking about. So a graph, in some sense, you can think of it just as a network here. Now you might be asking yourself, right, you know, you keep on using this word. I don't think it means what you think it means, right? Graph, right? We have 2 meanings for this thing here, and the answer is yes, you are correct. Just so you know, the word graph comes from chemistry. So this thing here, these molecules here, can be represented with diagrams like this, where each dot, every node there corresponds to an atom, and then you draw lines between them if there's bonds between them. So back in the day, these were called chemical graphs. And mathematicians were like, hey, that's a good name. Not really, because we already have a word for graph. But anyways, they were like, hey, we'll steal that word graph from you. And nowadays, there's different names that chemists use for these types of diagrams. But so that's where this word graph comes from. It actually comes from chemistry. And you might be asking yourself, why would anybody want to study these objects? Because graph theory is the study of this stuff. This is what I do for a living here, is study these objects. Well, the applications of this stuff are numerous. One huge application that we're sort of touching the surface of is there's an actual object called the Facebook graph. And what it is, it's enormous, right? Because there's millions of users on Facebook. And what you do, each user on Facebook gets represented by a dot, a node. And then you draw lines between dots if the corresponding users are friends on Facebook. And then you don't draw a line if they're not. This gives you some gigantic network that you can then study. And this is a huge, huge thing that people in marketing would like to understand, the dynamics of the Facebook graph, how it grows, or any social media graph in general, right? Because the idea is that if I can get somebody who's highly connected to a bunch of other people to buy my product, then that means that their friends are more likely to buy my product. So this tells me how to market my wares here, all right? So this also has sociology type implications here, just in trying to understand how to sort of humanity connects with one another on social media and the dynamics of that. So there's all sorts of applications of this in there. There's also computer science applications. As some of you have mentioned already, I teach a bunch of the math courses for CS at Grand Valley. And all I do in an entire semester is talk about how graph theory is useful to computer science. Algorithms, all sorts of stuff. I could spend a whole semester, because I do, saying this here, right? So we'll move on from that. There's also applications, really interesting scheduling applications. This is usually one of my favorite slides. Anybody? Airplane. Oh, so good. All right, anyways. So, right, as you can clearly see, my name is Roger Murdoch. I'm not Kareem Abdul-Jabbar. Such a good, anyways, whatever. Moving on. If you haven't seen it, this is a classic movie. All right, but there's applications in terms of scheduling. So say if you work at an air traffic control tower and you have a bunch of planes that are landing and or taking off, right? And there's scheduling conflicts because you can't have certain planes land and take off at the same time here, right? This can actually be solved using graph theory, in particular something called graph coloring, which is another one of my favorite things here. There's traffic problems that can be solved using graph theory. Dots represent cities. You draw lines between dots for various routes, and you can even weight them with certain values if traffic is heavy or not here. There's sports applications, another great movie. Sports applications that can be derived from graph theory, all sorts of things from a bunch of dots and lines. Yay, it's really cool. My kids look at me and go, wow, Daddy, pretty pictures, right? So just a bunch of dots and lines. There's all sorts of crazy stuff that you can do. Now, going back to our story with Erdős. So Erdős is looking for this object that we said was a cycle of friends, in particular a spanning cycle of friends here. So if we look at just sort of examining and making sure that we understand what we're talking about here, so hopefully you can see this here in red. Excuse me, this is another cycle of friends. Not spanning, but it's just a cycle of friends here, right? So Debbie, Eustace, Bob, and Debbie, they're friends. Here's another cycle of friends, Debbie, Clarice, Eustace, Bob, Debbie. Here's another one, it's a little twisted one there, right? A little twisty in there, it's kind of fun. It's another cycle of friends, and here's another one. This one is also spanning. It's kind of cool, right? So here's another way that Erdős could have arranged the people around the table so that everybody is happy with the person on their left and the person on their right. Okay, so again, this is what Erdős is looking for here. So he goes back to his diagram and is like, crud, how do I find this thing here, right? So there's a very natural question that arises, and that is, how do we know when we can find a spanning cycle of friends? How do we know when we can take a whole bunch of people and sit them, everybody in a party, sit them around the table so that each person is friends with the person on their left and the person on their right? Maybe surprisingly, the answer is hard. Right? And it's like, well, what was the point of this talk, right? Okay, answer's hard, right? And the answer is, it's in some sense, it's actually surprisingly hard because there's other structures that one can try to find in networks that seemingly are more complicated than a spanning cycle of friends, but are much easier to find. So this is a little weird. And this hardness here isn't actually just a graph theory question. It's actually very much a theoretical computer science question also. It is really hard, which is basically saying that the only way that Erdős could possibly determine whether or not he can do this, essentially, is by brute force. To just like try and seat people and hopefully he finds some arrangement that works, and if he goes through all of them and it doesn't, then oh well, he could be there for a while, right? So this of course frustrates Erdős, right? I mean, so he's sitting there, he's like, I didn't invite all these people, I got all these people in my house, you should see what they did to the bathroom, right? I got all this stuff going on, right? If you hosted parties, you have an idea of what I'm talking about here. Anyways, right? So this is what's going on. This is not my responsibility here. You know what I'm going to do? Forget it. Instead of trying to get everybody, I'm just going to take some people, I'll seat them around the table so that they're happy. Everybody else can just stick it and stand. It was a bad moment, all right? Bad moment, not his best moment here. So essentially, what is Erdős looking for here? He's looking for now a cycle of friends, just a cycle of friends, because he realizes trying to find a cycle of friends that spans everybody, that's hard. Forget it. Let's just do something seemingly, hopefully easy. Let's see if we can just make a cycle of friends here. Again, doesn't need to be spanning. This is actually quite easy to do. So easy, let's do it together. So this is where we get into group participation mode. So start to like, oh gosh, she's gonna ask a question, I have to respond. I hope somebody else says something, right? Yay, we all know this. All right, so what do we have here? So I have a statement that I want us to fill in the blanks for, okay? So I have two blanks, one up here, and the conclusion is we want to fill in these blanks in such a way that this conclusion is true, that we can find a cycle of friends. So the first line says, suppose we have a party with at least so many people. All right, so we're going to find a number that we can put in there that's going to make this work. And then, so we can call this sort of a party condition. And then we want to fill in this blank here. If each person has at least so many friends, then we can guarantee the existence of a cycle of friends here. So what I want us to do here, so think about this here. we want to find a number to fill in here, so the number of people we want to have at our party here, and then we want each person to have at least so many friends at the party, right? Because we don't want total strangers walking in that don't know anybody. That's awkward at a party, okay? Anyways, and in just real life in general, don't ever let anybody into your house that doesn't know anybody. I don't know, maybe? I don't know, just saying public service announcement. I don't know, whatever. All right, so let's think here. So let's go to the first blank here. So suppose we have a party with at least so many people. So here's my question to you. What is the smallest number of people that we need to even make a cycle of friends? In other words, what's the smallest cycle of friends? Smallest number of people that you can sit at a table so that each person is friends with the person on their left and the person on their right. We got a 2? We got a 3? Do I hear a 1? All right, 1, all right. So let's think about this 1, right? So what would that mean? It would mean I'm sitting at a table by myself. I'm friends with the person on my left. And I'm friends with the person on my right. Hopefully you are friends with yourself, right? Give yourself a big hug. Yeah, good job, right? In certain contexts, that is a cycle of friends. But for today, no. Okay? And we got a 2. Anybody else think 2? All right, good. What does that mean? It means you and a friend are sitting at a table. You're friends with the person on your left. You're friends with the person on your right. Give your friend a big hug. All right? In certain contexts, that's correct. But for today, we will say no. So the smallest will be 3. Okay? So the smallest cycle of friends will be something that looks like that. Okay? So that's going to be the smallest cycle of friends that we can do here. But again, there's actual active research that goes into allowing the other 2 conditions. Anyway, so yay, good for you. Good. So 3, we're going to put 3 there, all right? Now this next one here, if each person has at least so many friends, then we can find a cycle of friends. This little condition here is a little bit tricky, so I'll fill it in for you. I'll say this. So suppose we have a party with at least 3 people. If each person is friends with everyone else, then we can find a cycle of friends. I hope you believe this. Because if you're at a party, you got at least 3 people and everyone's friends with everyone, that's what it looks like. Pretty, huh? You could look at that for a while, right? It's actually really interesting. Total tangent here. This was not at all expected into the talk. What's actually really interesting is how your eye can see symmetry. Because the first time I did this, I drew this thing, which was maybe a couple of years ago, I drew this. Not by hand, like computers. Yeah, right? I noticed that it looked funny. And then when I went to the code, I was like, oh, it's missing stuff. And so it's actually really interesting how your eye can like sit there and go like, yeah, that looks right. That looks like that's got everything. Or all of a sudden go like, no, that doesn't have everything there, right? And rather than checking everything, your eye can like, there's also people out there, there's a thing called, this is definitely, now I'm really taking a tangent here. OEIS, the Online Encyclopedia of Integer Sequences. So it's an actual website. So people like record sequences and where they're found and things like that. There's a way to do a MIDI player. Some of you have no idea what I'm talking about. An old school little like audio thing. Beep, boop, 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 right? That sort of stuff there. So you can take sequences and you can like say, oh, I want numbers to have, these types of numbers to make this type of sound and whatnot and all this good stuff. And you can actually listen to sequences that shouldn't have patterns and all of a sudden your ear is like, holy cow, there's a pattern. Which is really weird that like visually you can't see a pattern, but your ear picks on something, picks up and it's like, oh, that's actually really interesting. There's something going on there. And then you try and figure it out. It's actually really cool. You could spend hours on this. Do your math homework first, all right? So there you go. All right, so anyways, so this statement here is totally true, right? All right, so we have at least 3 people at a party and everyone's friends with everyone else and we can find a cycle of friends, right? Yeah, we did it. We did it. Did it. Hooray. Dora? Yeah? Back, 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 back. Right. My kids love Dora. Kind of annoying sometimes, but the songs are so stinking catchy. So anyways, so yay! I hope this feels not very satisfactory to you. Because do we need each person to be friends with everybody else to make this happen? This seems a little much, just a little bit, right? So that's where we get into this. So this guy here, this is Professor Bruce Resnick. He is a professor of number theory at the University of Illinois, and over here is a stack of wood. He would love the fact that I'm like comparing him here with a stack of wood. No, really great guy. Love this guy here. Not a number theorist, but we became friends while I was at the University of Illinois because we're baseball fans, right? So he's a Cubs fan. I know, right? Ridiculous. Anyways, so one day we were talking and he was like, oh, hey, Mike, I'm going to be giving a talk to some undergrads a little bit later. And I just wanted to, I'm really excited about it. And I was like, oh, really? Yeah, that's cool. What are you going to talk about? He's like, well, I'm going to talk about research and math. And I'm going to say how it's like Jenga. And I was like, okay, cool. And so he told me a little bit about it. And then he walked away and I was like, I don't know what he's talking about, right? It took me a while, but I finally figured out what he was saying, and it makes total sense to me now. So if you're not familiar with the game Jenga, the way the game Jenga is played is you have a bunch of identical blocks of wood, and you start the game by just building a tower out of the blocks, right? So you make a tower out of all the blocks, and there's lots of variations of how the game is played, but the essential idea behind it is each person takes a turn by removing exactly one block from the tower, and you want to keep it standing as long as possible. Okay, so that's the idea. So you just keep removing block one at a time, right? And you want to keep the tower standing as long as possible. Now, of course, right, at some point in time, there's a threshold, right? There's some point where you're like, crud, I touch anything and the thing's going to fall, right? This is what we do in math. This is actually what we like to do as mathematicians. We like statements that are true, and we like to poke and prod at them until we get to a point. We like to play with these conditions here, and we like to weaken them a little bit, and maybe a little bit more, and a little bit more, all while trying to keep the end result, right? While still trying to get what we want, and seeing how far we can push it, and how far we can push it, and push it, and push it, and push it, until we get to a threshold, at which we know that if we touch any of the statements, then it becomes false. We're no longer guaranteed to get what we want. The tower falls down here. But we actually like to do more than that. We like to, when we get to this threshold point, sit there and go, why does the tower actually fall if I pull out one more block? Why does it fall? Can I tell where it's going to fall? So in other words, can I cheat, right? If I know it's going to fall this way, then while my friends aren't looking, I'm going to put my hand over there, right? And then like pull the block out and like, oh, hey, your turn. Right? I cheat all the time with my kids. Now, if they're watching this, boy, that's going to suck for me. Anyways, but this is what we like to do. We like to understand, we like to take statements and we like to push them as far as we possibly can until we can't push them anymore, and then we like to understand why we can't push it any further. Okay? So here was our statement. Right, that if we have at least 3 people at a party, and if each person is friends with everyone else, then we can find a cycle of friends. We have 2 types of conditions here. One condition is on the number of people in the party, and the other condition is this friendship condition on the number of friends that each person has. Now, we want to see if we can fiddle with these 2 things, all while still guaranteeing the existence of a cycle of friends, right? Now, we already talked about this number 3. We can't touch that Jenga block, right? We make it a 2. You're not going to, that can't happen. It doesn't work anymore, right? So that Jenga block here, that number, we can't touch that one. Tower falls. And we know why the tower falls, because you just can't even do it. It's not possible. But we also talked about this condition here, each person being friends with everyone else. And from the responses that I gathered from all of you here looking at this, we can do better than this, right? Each person doesn't need to be friends with everyone else at the party. And you're right, we can do better. So a person here by the name of Gabriel Dirac showed that if you have a party with at least 3 people, and if each person is friends with at least half the people, then you can find a cycle of friends. You can still do it. You don't need each person to be friends with everyone. I just need each of you to be friends with at least half the people, right? And it doesn't have to be the same half, right? I could be friends with one half, other people can be friends with another half, right? And so on here. Then you can find a cycle of friends. It turns out you can do way better than that still. You can get down to 2. I don't care how big the party is. It could be 1 billion people at your party, right? As long as each person has 2 friends at the party, you can find a cycle of friends. You can seat them around the table so that each person's happy. Let's prove it. Yeah, proof time, proof time. I made that one up. That's not a real Dora song. Anyways, so here we go. So here's our statements. We have a party with at least 3 people. Each person has at least 2 friends. We want to find a cycle of friends somewhere. All right. We got someone at our party. Alice. Alice has at least 2 friends. Bob and Clarice. Hello, Clarice. That's probably why I use Clarice for that name. It's another good but scary movie. Anyways, it still scares me to this day. All right, so let's take a look at Bob here. All right? How many friends does Bob have by our conditions here? By the conditions, not on the picture, but by the conditions here. 2, at least 2 friends, right? We know Bob is friends with Alice, right? So Bob has to have another friend. Well, what if Bob and Clarice were friends? What would we have? Our cycle of friends, right? Yay. So let's suppose that Bob and Clarice aren't friends then. If Bob and Clarice are not friends, then I have to have 4 people at my party, right? I have to have somebody else at my party then. Say Debbie. All right. How many friends does Debbie have by the condition? Right, at least 2. Debbie's friends with Bob. So Debbie has to have another friend. Well, if Debbie was friends with Alice, cycle of friends, okay? All right, well, what if Debbie wasn't friends with Alice? What if Debbie was friends with Clarice? Cycle of friends. Okay, so let's suppose that Debbie wasn't friends with any of those 2, which means that we have to have at least 5 people at the party. All right, so Eustace. Eustace has at least 2 friends. I hope this is starting to get deja vu here, right? Who's the other friend, right? Eustace is friends with Debbie. Well, if it was Bob, cycle of friends. If it was Alice, cycle of friends. If it was Clarice, cycle of friends. So if it wasn't, we've got 6 people at the party. And this goes on and 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 on. It's got to stop, right? You don't have an infinite number of people at your party. Right? That's one heck of a party, right? So at some point in time, it has to stop, say with Zach, right? Really creative. We're really, really creative with our names in graph theory. Right? At some point in time, Zach has to have some friend backwards, and boom, we create a cycle of friends. Okay? So that proves it. That no matter what, as long as you have a party with at least 3 people, right, and each person has at least 2 friends in the party, you can always find a cycle of friends. You can always find a group of people, seat them around a table so that each person's friends with the person on their left, the person on their right, and maybe there's some left over, right? Cool. This makes Erdős happy. Remember him? Remember the whole story that we were in here? Oh, it's been a while, right? This makes Erdős happy. Erdős is finally like, you know what? Maybe I went a little overboard with the whole, just only taking 1 table and doing this here. I got 2 tables in my house. So let's take 2 groups of people. Let's seat one of them around 1 table so that they're all friends with the person on their left, person on their right. And then let's see if we can find another group of people and seat them so that they're happy. And then we can have everyone else stand. So now we're looking for 2 cycles of friends. This is where it starts getting real fun. All right. So let's fill in the blanks now. Suppose we have a party with at least so many people. We needed 3 people to make 1 cycle of friends. How many do you think we need to make 2? 6. That was real good. Yes. All right. 6 people. Now, what do you think about the friendship condition? We needed 2 people to make 1 cycle of friends. Each person now needs to have at least 2 and 2, which would make 4. Yeah. Cool. Okay. Yeah, victory. Good. Good stuff. Erdős has a table in the basement. So now Erdős is like, hey, let's get 3 cycles of friends going. He's starting to feel really good about himself right now, right? So maybe, starting to feel his oats here. So, all right, so let's fill out the conditions. How many people do we need to make 3 cycles of friends? 9, right? 3 for each. And now what's the pattern? Is it 2, 4, 6, or is it 2, 4, 8? I just instilled doubt in some of your minds. It is 6. Yeah, it's 6. It's 2 for each, all right? Okay, good. All right, so awesome. So let's make a conjecture. In other words, let's make a guess. just a fancy word for guest. Like colleague is a fancy word for friend, right? Or somebody you work with. So here we go. So now what we're going to do is instead of looking for a fixed number of cycles of friends, let's let arbitrary number, k, x, whatever value, right? So we want k tables. How many people do you think we need to have at our party if I want k tables? 3 times k, boom, yeah, got it, yeah. Final Fantasy people, anybody play the game? A couple, all right, whatever. There's like a little bell, like after you win. That's all I think about when my students do really well. I go, yeah! I should have like a hot button like that I press on my phone that makes that noise. Anyways, whatever. All right, instead of the we did it. All right, whatever. So each person now, how many friends do you think each person needs to have at least? 2k, yeah. True story. This was actually conjectured by Erdős in the late 50s, early 60s. Good for us. That's pretty cool. So this was so this is now the true story part. Actual true story. That was a real conjecture, real mathematical conjecture, that if you have at least 3 times k many people at a party, each person has at least 2 times k many friends, and you can guarantee the existence of k cycles of friends here. And this was proved in 1963 by 2 people. This is Andres Heinel. I don't have a picture of Castelli-Corradi. I've looked all over the place, but there's no picture of him. But so they proved this. They showed that this conjecture was actually true using mathematical induction and logic and all sorts of other fun stuff here. Take discrete math. Yeah. So some of you I heard are in it. So yeah, good stuff. So this thing here, right? So this was actually proved. Now, of course, though, we have a true statement. Let's continue to play Jenga. See if we can do this here. So we have 2 conditions, right? This first condition, the party condition, 3 times k many people. I'm making k tables. Each table needs 3 people. I can't do better than the 3 times k. That's impossible, right? If I take 1 less, then all of a sudden some table doesn't have enough people on it, okay? So I can't touch this Jenga block. Well, what about this second set of Jenga blocks here? This was an actual question by Gabriel Dirac, who I mentioned before, and that is if we have a party with at least 3k people, if each person instead of has 2k friends, has at least 2k minus 1 friends, can we find the k cycles of friends? No, can't do it. Tower falls. Okay, so we hit the threshold. We found the threshold. The threshold was 2 times k, right? If each person has at least 2 times k many people, we can do it. But if we go any lower, we remove any Jenga block, a single one, tower falls. We are no longer guaranteed to get k cycles of friends, okay? Why? Well, that question was answered last year. So this is where we get into 1963, last year, we got the answer to the question. The answer to the question, so this is Hal Kierstead, professor at Arizona State University. This is Sasha Kostochka, professor at University of Illinois. He was my advisor. I love him, so cool. Like a big Russian teddy bear. I hope he does not find this video. And this, holy cow, I just realized that. Anyways, right, so Elise Yeager, a good friend of mine. She was also at the University of Illinois, another student of Sasha's. She's at the University of British Columbia over in Vancouver. And so they proved last year that the only thing, what makes the tower fall, is there's a large group of people at your party that don't know each other. Which in some sense kind of makes sense, right? So you got a party with a bunch of people and you want to seat people at tables. If there's a bunch of people, large is of course unspecified, I'm avoiding technicalities here. If you have a large group of people that don't know each other, then those people, they shouldn't get seated next to each other, right? Because if they do, then this breaks the pattern that you want. So if you have a huge number of people there, that becomes difficult in you trying to seat people at tables here, okay? So that's kind of a problem. And in fact, so they showed that you can cheat the Jenga game, right? So you can cheat the Jenga game. 2K is the threshold. But so long as you run around and start introducing people to one another, So that you avoid this large group of strangers, you can pull one more block out. And you can make it fall down. You can make it work or without falling down. You can get one more block out so long as you know you don't have a large group of people that are complete strangers at your party. What happens if you go further? Welp. So that's me. And that's my friend Theo, Theo Mola, who's at the University of South Florida. We showed that that's the only thing that's keeping you from going down. A lot of technical stuff here. But what it's saying here is that I don't care how many Jenga blocks you want to pull out. You just got to make sure that you don't have a large group of strangers. It's not just one block. You can pull 100 blocks out. Doesn't matter. As long as you make sure that you don't have a large group of strangers, again, avoiding the technicality there, then you will be guaranteed to seat the people at your party that you want to here. Which is kind of cool. I thought it was cool. That's why I even worked on the problem. Was like, I don't know what happens beyond 2k minus 1. Well, let's find out. And we did. That was sweet. That was all cool. We're still finishing up cleaning this thing up here. Now, you might be asking yourselves, oh, good, I have time. Yes. I was worried that I wasn't going to have time here, right? What did we do here? We had this, so this story, in some sense, you might think comes to an end, but it doesn't. But wait, there's more. I feel like I'm selling you like Ronco knives here, right? Some of you haven't stayed up late enough and watched infomercials, right? But wait, there's more. I'll throw in more stuff that can be done here. And since I have time, let me tell you about it. Here's the fun. All right, let's see if you can find the pattern. The pattern is so cool. Okay, so K cycles of friends. Okay, this happens when we have at least 3K people, and each person has at least 2K friends, right? This is a true statement. It's right at the threshold. There's another object, another structure that we are interested in looking at. It is called a chorded cycle of friends. Chorded has to do with, if you remember geometry, you have a circle and there's a line segment with both endpoints on the circle. They call that a chord. So here's an example here. A chorded cycle of friends, you would have 6 people that form a cycle of friends, and then you have a pair of people who are friends across the table. So this is an example of a chorded cycle. This is an example of a chorded cycle. That's an example of a chorded cycle. Just so long as I have a cycle of friends, and then there's 2 people at the table who are friends across from the table. Okay? Let's find these. Okay? So K chorded cycles of friends. Okay? What is the smallest number of people that I need to make a chorded cycle? Does 3 work anymore? 4, right? 4 is the smallest number of people to make a chorded cycle of friends. It looks like this, right? So I have 4 people, and then boom, just one other friendship pair there. So how many people do you think I need to make this happen if I want K of them? 4K. Yes, you're right. All right, and each will need at least, what's your guess? Somebody just make a guess. 3 is right. It's 3 times K friends. And that's the threshold. That's creepy, right? This is a true statement. We know what happens when you pull one Jenga block from this. This is actually something that myself, Theo, and Elise did a couple years ago, but we have no idea what happens when you go below that. Don't know. Weird. Oh, I still have time. Weirder stuff. Okay. That's a chorded cycle. A doubly chorded cycle. We are really good at names, okay? Means that you have a cycle of friends, and then you have 2 chords, right? We're really creative, right? So that's an example of a doubly chorded cycle. Here's another doubly chorded cycle, right? Okay. So, okay, doubly chorded cycle, the smallest one has how many people in it? Okay, you might think 5, but can I do? It's still 4, right? Okay, cool. So here we go. If we want K doubly chorded cycles of friends, then we should need at least 4K people. I did not write that wrong. That's a 6. I don't know why. Nobody does. We don't know. We can't get it down to 4. And by we, this is a group of people, 3 people who did this from Georgia Tech. We don't know. We don't know why we can't get it down to 4. It should be 4. It should be 4. We don't know. Don't know why. I don't know. Weird, right? This is why I do what I do, because it's like, I don't know why. Well, wait, there's more. All right, so I'm not going to do another structure, because then that starts getting weird. Okay, but now let's say, hey, you know what? Instead of, why should I want every table to form a chorded cycle of friends, right? Or every table form a cycle of friends? What if I want a combo pack? Right? Mix it up here, right? Rather than buying like all AA's and all AAA's, why can't I just buy like one pack that has some AA's and some AAA's in it? That'd be more useful sometimes, okay? So what if we had something like that? So now let's suppose we want, I don't know, let's use R cycles of friends and T chorded cycles of friends. Somebody make a guess how many people you need. 4. Oh. How many for the cycles? 3 for each of them. How many for the chorded cycles? 4 for each of them. It's weird. It literally is the addition of those two. And each person needs at least how many friends? 2R plus 3T. That's right. That's absolutely right. 100% correct. No. Isn't that weird? That's so weird. That the best thing for these things turns out to be the best for the combo pack. That's weird, right? So cool. I think this is like where I was telling you at the start, like this gets me all giddy, right? This is so cool because in some sense, some weird way, it makes sense, but I don't know why it makes sense. So I flip back and forth from like, oh yeah, it totally makes sense to like, no, it doesn't. Why should that work? And I keep flipping back and forth. And there is an absolute amazing thing that actually happens here because this, if you look at this thing here, what if I say T is equal to 0? Then all I'm looking for are cycles of friends, right? And that's exactly this thing. And if R is equal to 0, then all I want are chorded cycles of friends, and that's exactly this thing. So this is actually a transition between those two states. So weird. So cool. But that's what happens here. And we don't know we know what happens just beyond this. Only a little bit, though, because it's weird stuff. But we don't know what happens beyond that, farther beyond that. There's so much stuff here that we just don't know. And there are patterns here. Okay, there are patterns here that we can see, and then there's just something weird that happens here that we have no idea why. No clue, you know.
Do you have a specific definition for like the large groups of strangers?
Yes, we do. Yes, avoiding it, but yes. It's actually not that horrific. I'll write it here, so for those of you who want to check out. So if n equals number of people at party, then you want to make sure that you have less than n minus 2k plus 1 strangers. That 2k comes from there. And that n is the number of people at the party. It's weird. And the number of strangers for here is n minus 3k plus 1. And the number of strangers here is n minus 2r minus 3t plus 1. Weird, right? All right. I think that for me, I think I'm at my threshold. All right, that's it.
Any questions for Dr. Santana?
Is there still progress being made on the original Ernest question of the?
So no. So it's not so much that as it is, okay. So the answer to that question is yes and no. So yes, there is still stuff that's being done. The stuff that myself and my friend Theo did is the most recent stuff on this here. In addition, in terms of this exact one, where all you want are cycles of friends.
I meant the question that you asked.
Oh, the spanning one? Yeah, so it is hard. It is definitely hard. So there's a ton of work that's being done on that. In terms of what people start to look at, it gets so fun. I could spend so much time talking about this. So that is a property that's called Hamiltonicity. So if you want to look at that, that's the property I'm actually talking about. It's the fancy term for it. But so what people have been doing is they say, okay, in a general setting, I can't find a spanning cycle of friends. But what if I restrict the structure on the party? Meaning that now I'm being super restrictive with the people that I'm allowing into my party, that they have to, that certain things have to be avoided. So for example, I want to avoid somebody who knows 3 people who are complete strangers. This may seem like really silly that on the surface. This is actually one of the most prominent restrictions in all of graph theory. This is something that's called the claw. Scared of the claw. That was a Jim Carrey movie. I can't remember which one. All right, but I think it was just one finger. But anyways, right, so this is called the claw. If you try to restrict this here, so these people are not friends, right? If you try to make sure that this never happens anywhere in your network, can you determine whether or not there's a spanning cycle of friends? There's actually a huge, huge conjecture also in that area as well. So we ain't done. Yeah, we ain't done by any means. That's a good question. Yeah. Any other ones?
When you started your talk, you indicated that perhaps community college was a defining moment in your higher education, maybe the defining moment.
Yeah.
So what's your defining moment in terms of what got you interested in graph theory?
Good question. What got me interested in graph theory was it's actually kind of funny. So again, from Southern California, the weather is gorgeous, right? 80% of the time, the weather is beautiful. 15% of the time, it's too hot, it's too cold. Too cold meaning like we have frost in the morning, right? I laugh at my dad every time he goes, oh, it's so cold out here. Dad, it's like 8 is the high, you know? And then there's wind chill, Dad, really? The other 5%, I didn't get to 100, right? The other 5% we're surrounded by walls of fire, okay? So what's actually quite interesting is that when I took my first discrete mathematics course, we had a firestorm. Classes were canceled for a week. That was the week of graph theory. So I didn't learn any graph theory in my discrete mathematics course. And what happened was the next year, I got involved in a program that said, hey, you need to have a faculty mentor because it's a really good idea to have some faculty member that you can go to and talk to. And I was like, okay, cool. So I picked one of the professors in the department that I had taken some classes from that I really liked, and I said, hey, this program needs me to have a faculty mentor. Would you be my mentor? And he said, sure, but do you want to do some math? Like, yeah, okay, cool. So we did graph theory. And that was what started it. I ended up working with this faculty member whose area was graph theory, and we we started doing stuff, and I ended up proving a result like a few weeks later or something like, well, not really a few weeks later, but it was already known, something that was already known, and gave a talk on it and things like that. And that was really the defining moment for me, that it was like, wow, this is kind of fun. I can draw pictures, which is great, and I don't have to take integrals, which is super great too. Not that integrals aren't great, but they're fun, right? But like, yay, dots, lines, so cool. So for me, that was really the defining moment for me in terms of my academic, my graph theory career. And that particular advisor, he and I are still friends to this day. I just got an email, Christmas email from he and his wife and stuff, and just great people. Yeah.
Yeah, going into such like a highly theoretical field, what is the transition between doing research in stuff that has already been worked on and doing original problems?
Okay, I thought you were going to ask the other question. So the other question is how was the transition from not theoretical to theoretical? That was what I was laughing about. It's like, that wasn't fun. I can tell you that one also. But so in terms of going from non-original to original research, that was an interesting one. I will say that it happened naturally for me in some regards because of the way that I approach my research. Not everybody necessarily does this, but the way I sort of approach my research is, what do I want to know about? And what do I think is interesting? And I start to look into it, and I start to look at this stuff. I mean, this is why for me, this stuff is so interesting to me, right? This is why I was getting all excited there at the end. So this is why I do a lot of this in terms of my own research, is because this is exciting to me. So there was that. The major hurdle that one will find in going from doing stuff that was previously done to stuff where the current research is nowadays is one of the things, and this is irregardless of any field, is that now what's happening, and I think it's actually really cool, is that a lot of the really current, like, big things that are being proved, like stuff that you'll like actually see like on the news, right? It's like, oh, somebody proved something great, right? And the population has no idea what they're talking about in general, right? Which is fine. But what's usually used are tools from different fields of math, which is actually amazing. It's the idea that what I didn't realize in graph theory is that if I wanted to really do some cool stuff in graph theory, I actually needed to be good at probability, which is kind of weird. But there is some crazy stuff that you can prove using probability. There's stuff that involves other fields like number theory and other things like that, which is one of the great things about, being a math major, right? You can take, as you go on and transition from the non-theoretical to the theoretical stuff, right? And you start taking like geometry, and you start taking, other courses here and courses there, right? And then it's like, you start to every now and then start to see, like there's a theme. Like originally they seem like different pieces of like different tapestries, but they're actually different pieces of one tapestry, which is kind of really cool. So in my advice for people who want to sort of transition from, older stuff to newer, more cutting edge stuff is like, actually go and look at other areas of math, because you never know what tool you might pick up over here that all of a sudden like, oh, well, that makes sense over here. One of my favorite, funniest talks I ever went to, and I went to a number theory seminar talk, graph theorist. I don't go to number theory seminars. The reason I went to this talk was because the speaker was talking about graph theory, and he was making fun of graph theory people at the start. He says, so graph theorists have this object that they call, this is actually how he talks. Graph theorists have this object that I didn't say his name in case he would watch. This object called a hypergraph. And these edges and hyperedges and things. Well, we call these hyperedges sets. And they, for some reason, call them hyperedges. I don't know why. And these vertices, we call them numbers. And it was just one of those things where it's like, if you can make the translation between the two fields, it's like, oh, so the stuff you're talking about, this weird terminology actually just means this, right? And it's like, oh yeah, we have tools for that stuff. And then when you transition it over, it's like, oh, we can prove all sorts of crazy things. So that's a long-winded answer. Sorry. I talk about myself a lot. I said that at the start.
Thank you so so much. It was
No, thank you.
Very enjoyable. I'm sure that the speaker will probably stick around for a few minutes in case you have additional questions.
Yeah.
I was wondering why you used Eustace.
I'm sorry, what?
Eustace.
Oh, Eustace. That's a good question. Where have I heard the name Eustace before?
That doesn't require definitive answer.
Oh, yeah. That's a good point.
Thanks. Please help
Yep.
yourself to some pop and cookies on your way out to the lot here. Our next talk is tentatively scheduled for E-Day, which is February 7th, 2018, 2718.
Oh, man.
I know for sure January 29th, what's going to happen with that. So stay tuned. Thanks for coming, everybody.
Okay, thank you.